Have any questions before we get started?
No questions about the material. I have a question about the exam
Okay.
um, on the long form answer. I was wondering if you're ever planning on working that in a video. I ended up getting the three-step paragraph, the paradigm answer
Oh, gotcha.
question, and I don't just personally I was able to get the right answer on the multiple choice. So the first part of it went okay, and then it just went off the rails on me. The rest
Yeah,
of the
that's
math
the
went
vast
off the rails.
majority of people had the same problem, so don't feel too
Okay.
horrible about it. But yeah, I actually have already worked it. In fact, there's several instances of it on my
Okay.
YouTube channel. But I'll
Okay.
certainly, if you want to, set up a Zoom meeting or anything, I can meet with you sometime and walk you through it step by step if you want. That's not a problem. I love doing that stuff.
Yeah, let me
We can
take a
do it
look
with
at
all
it.
three versions.
Okay. Yeah, let me take a look. I mean, I did watch the videos, so I think I understand it. What threw me off was actually just going to L and L squared as the area. Let's think kind of the step that makes sense to me. But I'll go back and take a look at it and see if
Yeah,
I can figure
it
out.
sounds like you're getting it a little better than most. So I mean, definitely pat yourself on the back with that. But yeah,
Okay.
also if you do a search on my YouTube channel and just do Paradigm
Yeah.
Paradigm, that should pop up several instances of me doing that, and just
Okay.
find the one you want or you like best.
Yeah. Okay. Sounds good.
Yep.
Yeah.
I wouldn't mind doing it again now. I'm just a little bit behind time, so
Yeah. No.
I
Not
wouldn't want
no.
to do it until after
That's
class.
fine. Yeah.
Gotcha. All right. Well, it is already 5:22, so I guess I should just go ahead and get started. Josh and other people may or may not show up, but I know they'll watch it later. So we did have one problem that I chose not to work in chapter 25, but really, in retrospect, I think it would be best if I worked that in this setting as opposed to just allowing you to read the example, or as opposed to uh, me just referring you to another video. There's a little intricacy of this calculation, so I just thought I'd do that, and it'll be the final problem from chapter 25. Just again, I think the example that the book has is plenty good, and this is very much like that. But I wanted to explain it to you, so we'll go ahead and get started. I'm going to start by sharing my iPad screen, and I'm going to say that out loud so I'll remember to do it. I really think I'm the funniest person in this, at least in this Zoom meeting. If I, even if I'm the only one that laughs
Agreed.
at me.
Agreed. I'm laughing with the mute on.
I feel you. All right, what I have here, it says a copper wire with a 2.94 millimeter uh, diameter carries 4.00 amps of current. A, what is the average current density of the wire while it carries the 4 amps? B, estimate the speed of the free conduction electrons uh, VD, which means drift velocity, and C, for comparison, what is the root mean square velocity for an ideal gas of electrons at 20 degrees Celsius? They often call that thermal electrons. So if you ever hear that phrase, that's what they mean. Just electrons that only have an energy associated with them having a temperature greater than 0 Kelvin. So I mean, I just wanted to use the typical equation that we derived sort of last time, and I'll start off with that. So our solution is going to entail, of course, the equation, but it's also going to tell us that I is equal to 4.00 amps. We have the diameter as 2.94 millimeters. So I could, in fact, go ahead and divide that by 2 and make it the radius, but I like to occasionally use the formula for area, which is pi r squared, and just replace the r with d over 2 so that everybody sees it's actually 1/4 pi d squared. So that's, just something that you can avoid taking the time to divide by 2 each time, that sort of thing. Uh, we do know it's copper. I tell you, I know that I will need the density and the molecular weight of copper, so I'm going to go ahead and write that. So the density of copper is 8.9 times 10 to the third kilograms per cubic meter. And again, that's just the density of copper. And then the molecular weight of copper can be looked at two different ways. In this particular example, I'm going to start off using it the traditional way that you learned in chemistry, which was when you read a atomic weight off of the periodic table. For instance, the weight of copper is 63.5. There's at least a couple ways of looking at that. One, it's 63.5 grams in a mole. So you can look at it as just 63.5 grams represents the mass of 1 mole of copper. Another way of looking at it is 63.5 grams per mole, and then that does the same thing as the previous one. But then another one is that it's 63.5 U, which is the unified atomic mass unit. And in that sense, it's saying a single copper atom has a mass of 63.5 unified atomic mass units. I'm choosing to use either the first or the second version in this particular example. So I also need to know the equations. What we know is that I technically is equal to the integral of J dot dA. In that sense, it sort of looks like a flux type thing, except, flux was just calculating a field of some sort through a surface. And in this case, we're imagining sort of a surface. It's the cross section of a wire. So if you imagined taking a long straight cylindrical wire and slicing it in half, dead center and perpendicular to the rotation axis, to the symmetry axis, it would make a circular face. That is the surface I'm integrating over in this j.da, but it's rare that you actually have to do the integral portion. You're normally just going to say, on average, I is approximately j times a. So that's another way, and I could just put a bar over it to represent the I as an I average. So that's a couple expressions, and we also sort of worked out that J is actually equal to negative times N times the magnitude of the charge of the electron times the drift velocity, and in that sense, is a vector equation. I want to point out that the N is supposed to be the number of free electrons per unit volume. So that's what that lowercase n is. We derived it by basically imagining a little stretch of wire that is a length L, say, and has a cross sectional area A. And we basically said, well, what's carrying the current is what we would call free electrons. And those electrons are just drifting by in the same direction as, or actually in the opposite direction of conventional current, but in the same direction as real current, and they're moving that way. So, in order for us to calculate the drift velocity, we had to sort of calculate how many free electrons there would be in that little length of wire. So, we started off saying that the current would actually be capital N, the total number of free charges, times E, the charge, or actually technically times parentheses negative E, the charge per carrier. And then that would actually give you the number of coulombs. And in order for it to be an actual current, you'd have to have it per second. So we went on and worked that out and came up with this formula as the part of J. So that's what we're going to use. And what I want you to do to imagine this is, in order for us to calculate the drift velocity, we need to have the J. And in order for us to calculate the J, we can use this simple expression, which says on average, I is equal to J times A. So I'm going to start off with part A, where it says, what is the average current density? I'm going to start off with that and realize that J on average is equal to the current divided by the cross-sectional area. And that, of course, is going to be 4.00 amps, which remember is coulombs per second. And all of that will be divided by 1/4 pi d squared. So we're going to say 4.00 amps divided by, well, actually the 1/4 in the bottom will make it a 4 in the numerator, so I'll put a 4 up there. And that 4 can be considered an infinite number of decimal places, just for sig fig characterization. 3.14159 is way more sig figs than we have, so that's sufficient for the pi. And then I'm going to say 2.94 times 10 to the negative third meters is the actual diameter. And of course, that has to be squared. So all I have to do is take 4 times 4, which is 16, and I'm going to divide that by parenthesis 3.14159 times 2.94 times 10 to the negative 3 squared. I close parentheses and say equal, and I get 5.8922 times 10 to the fifth, and that is amps per square meter. And obviously, I used two additional figures that were not significant, as I often do. So we now have the answer for part A. That is what J is. Not only that, having J, we can now use this equation to figure out the drift velocity. So, how do we go about calculating N? Well, N is equal to the number of free E minuses per unit volume. What we know is that 63.5 grams of copper implies Avogadro's number of atoms of copper. Now, I didn't state this, which I should have written it in there. Let me go ahead and do that now. Assume copper offers one free E minus per atom. Now, that is in some sense, that could be something you consider a measure of the conductivity of a metal. One with good conductivity means it's a good conductor. And if a particular metal was able to release 2 electrons per atom or 3 electrons per atom, you'd think the 3 would be better than the 2 and the 2 would be better than 1. In this case, we're just calculating it as if it's 1. The more general answer to this problem is we have to let you know exactly how many electrons per atom will be released by a particular conductor unless you are in the field of material science and have some way of knowing that and stuff of that sort. So what I'm going to do is calculate the number of atoms per cubic meter. And then, since the number of electrons is 1 per atom, then the number of electrons is the same as the number of atoms. So by me knowing that 63.5 grams of copper has Avogadro's number of atoms in it, then I can tell basically the number of atoms per gram or the number of grams per atom, any way I wanted to say it. So if I look at it that way, then I'd say 63. Ooh, let me get back to my green. 63.5 grams uh, has, oops, 6.0221 times 10 to the 23rd atoms of copper in it. So that's just me restating what Avogadro's number is. Now, what we want to do is we want to find some relationship that could relate, which, right now we have like grams per cubic meter or excuse me, grams per atom or atoms per gram. But what I'd like to do is find some relationship between that and, for instance, the volume. Well, that should make you think of density because density is equal to mass over volume. So you could actually make the argument that mass would be the density times the volume. And what we know is the density of copper is equal to 8.9 times 10 to the third kilograms per cubic meter. So if we took and imagined a chunk of copper that was 1 meter by 1 meter by 1 meter, then we'd know that chunk of copper would weigh 8.9 times 10 to the third kilograms. We'd also know if we divided that kilograms by the number of grams in a mole, we would actually be able to figure out how many moles there is in it. And since we'd also know how many atoms are in a mole, we'd also know how many atoms per unit volume. So what I'm going to do is I'm going to take and say N is going to be, uh, let's look at it this way. I want the grams per cubic meter. So I'm going to take the density of copper and I'm going to divide that by the molecular weight of copper. And that molecular weight of copper, of course, is just going to give us the uh, it's kilograms per cubic meters divided by essentially mass. So this would, in some sense, be a way to just calculate the number of atoms per cubic meter for a specific Avogadro's number. So we just have to remember that, in fact, in order to get this to the number of atoms, we can't just use the atomic weight. We have to divide the atomic weight or atomic mass by Avogadro's number, because when you divide the mass by Avogadro's number, the 63.5 grams, you get the mass per atom. Does that make sense? So this is going to become Avogadro's number times the density of copper divided by the molecular weight, and we'll just follow out the units and see if it works right. If it does, then we'll be confident that we calculated the lowercase n correctly. So Avogadro's number is 6.022 times 10 to the 23rd, and that's usually just in reciprocal moles. But in this case, I'm going to say, since it's the number of atoms and since the free electrons is 1 electron per atom, I'm going to go ahead and say that's electrons per atom, or excuse me, per mole. So this is E minuses per mole is the units for Avogadro's number in this case. It's usually, like I said, just reciprocal moles, but you can read that as atoms per mole or molecules per mole or whatever. The density is 8.9 times 10 to the third kilograms per cubic meter, and then dividing this all by 63.5 times 10 to the negative third. Notice it was 63.5 grams is the atomic weight of 1 mole, or the atomic weight of copper, which is the weight of 1 mole. But since that's in grams, I need to convert it to kilograms because the number I have above is kilograms. So you can now see that basically what we're going to have is the kilogram is going to cancel out with the kilogram, and the mole doesn't really matter too terribly much. That just gave us a number, but we will get E minuses per cubic meter, and it technically says per mole, but that's good enough. So if I take this calculation, I get 6.0221 times 10 to the 23rd times 8.9 times 10 to the third. Now I'm going to divide that by 63.5 times 10 to the negative 3, and that would give me 9.29. Whoa, Nelly. That would give me, dang it, switched to the wrong color. Gives me 9.2939, two extra digits again, times 10 to the 28th, and this is E minuses per cubic meter. So now we can go ahead and say, well, J in magnitude is just equal, notice I'm dropping the negative sign here, it's just equal to N times E times VD. So the drift velocity, VD, should equal J over N times E. So that should give me VD is equal to the J, which we found was 5.8922 times 10 to the fifth amps per square meter. Now I'm going to divide that by the N, which we just found was 9.2922 times 10 to the fifth amps per square meter times 1.602 times 10 to the negative 19th coulombs. And remember, an amp is a coulomb per second, so dividing amps by coulombs just gives us reciprocal seconds. And then dividing meter squared in the denominator, or excuse me, yeah, it's meter squared, and the 9.29, oh, that was meter cubed. Sorry about that. I wrote down here that it was meters squared. I don't know why, but it should have been meters cubed. And the reason why I'm pointing that out is you can see that the meter cubed will come on the numerator and the meter squared will be in the denominator. And a meter cubed divided by a meter squared is just a meter. So I've got a meter in the numerator and a second in the denominator. So it does give me meters per second. So now I'm going to take that figure 5.8922 times 10 to the fifth. That's the actual current density. I'm going to divide that by parenthesis. Uh, I'm using the previous answer that I had, so I'm just going to pull up answer. And then I'm going to say times 1.602 times 10 to the negative 19th. And what we get is 0.00. Actually, I'm going to go ahead and write it in scientific notation because otherwise it's just not too pretty. So I'm moving the decimal 1, 2, 3, 4, 5. So it's 3.95 74 times 10 to the negative fifth meters per second. So it's on the order of 39 or, well, 40 microns per second. Not hugely fast, but it is moving anyways. And what you'll see in a second is it's actually moving quite slow if you compare it to thermal electrons. So that's the next step is use what we learned from chapter 17 or 18 and calculating the thermal velocity of the electrons, treating it as an ideal gas. So anybody understand? Anybody have any questions about those two parts so far?
Yeah, just could you back up to density equals mass over volume and how you walked that to the
Okay.
density equals 8.9 times 10 to the third?
Yeah, that's no problem at all. So, density is equal to mass over volume. That's just our definition of it, obviously. You can even tell from the units, it's kilograms per cubic meter. But if you think about it for a second, and let's say this is true about any collection of copper whatsoever. So, why not imagine exactly how big would be a 8.9 times 10 to the third kilogram chunk of copper? If you made it perfectly cubic, according to the density, it would be 1 meter wide by 1 meter deep by 1 meter tall, and it would weigh 8.9 times 10 to the 3 kilograms. So that is a very specific chunk of copper that we can think about. Any chunk of copper will do. We just have to know the density for the given temperature we're dealing with, and we're pretending like everything's around 20 degrees Celsius. So we're doing that. Now, if you take and divide that 8.9 times 10 to the third kilograms, that big 1 meter by 1 meter by 1 meter chunk of copper weighs, if you divide that by the mass per atom, then you'll get the number of atoms per cubic meter because remember it's already a cubic meter. So to get the number of atoms, you have to take the molecular weight, which is 63.5 grams, and divide it by Avogadro's number, and that would give you the actual mass per atom because 63.5 grams is understood to be Avogadro's number of atoms. That's the definition of a mole. Does that make sense?
Yeah, I got it. I think I missed that density of copper was given.
Oh, gotcha. Yeah.
Okay. All right. Yeah.
Yep. And this is more of a thing where it's not so critical that you didn't think of it yourself. It'd be great if you did. But now that you've seen it, you just want to remember that's the trick. You're going to take the density divided by the molecular weight. And if you think about it in the other ways, see, I was treating the molecular weight as grams per mole or the grams in a mole. You can also think, wait a second, 63.5 grams is one version of what the periodic table tells us, but the other version is that it's 63.5 atomic mass units per copper atom. So if you just converted the 63.5 atomic mass units to kilograms, what you'd end up getting is basically the same thing as dividing 63.5 by Avogadro's number, because it turns out the conversion factor, the 1.6605 times 10 to the negative 27th kilograms that we associate as the conversion factor between unified atomic mass units and kilograms, if you look at that number, that is just 1 over Avogadro's number. But when you do it, if you just took 1 divided by 6.0221 times 10 to the 23rd uh, moles, reciprocal moles, if you just did 1 divided by that, you'd get 10 to the negative 24 instead of 10 to the negative 23. And that's because you're doing grams instead of kilograms. So the only difference would be you have to convert that back to, instead of grams per mole, to kilograms per mole by multiplying it by or dividing it by 1,000. So that's where that 1.6605 times 10 to the negative 27th comes from. You just take 1 over Avogadro's number, assume it's coming out in grams, and then convert it to kilograms. Does that make sense?
Yep. All good.
All right. So now what I'm going to make use of is the fact that we knew from early on, I'm going to write it up here in red. We know that 1/2 m v root mean square velocity squared is equal to 3/2 kT. That's what we derived for an ideal gas in chapter, I want to say it's 18. So what that means is the root mean square velocity, v root mean square, is just equal to the square root of 3 kT over m. So all I have to do to calculate the root mean square velocity of the electrons at 20 degrees Celsius is put in K, the Boltzmann constant, which is 1.6307 times 10 to the negative 23rd joules per Kelvin, and put in the temperature in Kelvin, so that'd be 293 Kelvin, and then divide it by the mass of the electron, which would be 9.109 times 10 to the negative 31st kilograms. So in doing that, I'm going to say VD is equal to the square root, and I'll put all this way, 3 times 1 point, uh, I should probably double check just to make sure that that is the number, 1.6307 times 10 to the negative 23rd joules per Kelvin times 293.15 Kelvin. And then all that would be divided by 9.109 times 10 to the negative 31 kilograms. Of course, we're still taking the square root of all this junk. So that's what the answer is going to be. I'm going to go ahead and do that calculation now. I'll say square root, and the numerator is 3 times 1.63. I really need to check that. Let me pull up something real quick. For some reason, I'm drawing a blank on K, the Boltzmann constant, and I shouldn't be, but anyways, I am. So I want to make sure I don't put it in wrong. I have it right here. Oh, there it is. Sadly, this is one of the things that I review on a daily basis just to keep my brain up to snuff. And I hate it when this happens. 1.3806. Yeah, so that was good. I think that was why I recently learned that it's 3806 and I'd been doing 3807 for so long. So 1.6306 is what I'm putting times 10 to the negative 23rd. That's 3 times K times 293.15. Now all that is going to be divided by 9.109 times 10 to the negative 31. All that's still under the square root. And in fact, I end up getting 1.2 times 10 to the fifth, or 1.3 times 10 to the fifth meters per second. That's the thermal velocity of electrons treated as if they're an ideal gas at 20 degrees Celsius. So what we're saying is, in general, the electrons are acting somewhat like a sea of ideal gas electrons. In other words, an ideal gas made of nothing but electrons. And if they are acting that way, then they're moving around at 100,000 meters per second, whereas the drift velocity is a meager, 40 microns per second or 40 micrometers per second. So you can see this drift velocity is really, really small, but that's not really a thing that causes light to go or that causes electricity to be delivered slowly or anything. You can sort of think of it as if you took a long water hose and you found exactly the right types of marbles that would fit in the water hose. If you stuffed that water hose with a endless string of marbles until basically the last one you put in one end caused the first one you put in to peek out the front of the other end of the water hose, then even moving at a micron per second, if you push that marble into that back end, that other one would instantaneously pop out the other end. So you could still get nearly instantaneous motion. It's just a fact that it's going slowly in individual pieces. So hopefully that makes some sense. Anybody have any questions on that one? I'm sorry for fitting that calculation in the bottom. I knew I'd already written the next one and I didn't want to have to stop and make up another sheet on my iPad. So I just fit the calculation in the bottom. And that does seem consistent with the answer I got the previous time when I calculated it before class. So I think that's all good. Let's move on to chapter 26. So, chapter 26 is called DC Circuits, and it starts off, as always, with a chapter opening question that I'm actually going to work as an example problem. But that's always something you want to address. Now, the sections in chapter 26 are EMF, what we call electromotive force, and terminal voltage. The terminal voltage I've hinted at before. Basically, if you take a brand new battery, a AA or AAA, a C or a D battery out of the package, I told you the nominal voltage is supposed to be 1.5 volts, but when you first buy it, if you just put a voltmeter or a multimeter on it and test it, what you'll find is it might read 1.72 volts or 1.68 volts, and it's going to read that for some time. But once you start using it, it'll slowly that number will slowly decrease over time. But even when you get it brand new, if you actually connect that 1.72 volts battery up to a load like a light bulb or a resistor or something like that, if you then measure the terminal voltage, the voltage between the positive terminal and the negative terminal of the battery, while current is flowing out of it, you'll find that it's not 1.72 volts anymore. It'll be a little bit smaller. So that's what terminal voltage is about. The second section is resistors in series and parallel. I'm not going to do the derivation like I normally do with that. Because you guys have covered that in lab already and should know it. So I'm just going to go on the assumption that you guys know that when any number of resistors are in series, the net resistance is R1 plus R2 plus R3 plus dot 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 on up to Rn. And when they're in parallel, it's 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot dot dot. So we're going to just blow through that part. Then we get to section 26.3, which is Kirchhoff's rules. This is the same Kirchhoff that has rules that are listed in astrophysics and astronomy, just telling you again what brilliant people these are that we get to have their names in our books, specifically because they had their knowledge base extended to so many different fields. So you were looking at hot objects glowing, and they put out three different types of spectra. That's Kirchhoff's laws. Well, guess what? There's also Kirchhoff's rules, which is a conservation of charge and a conservation of energy that tells you how to analyze circuits. After that, 26.4 is talking about electromotive force in series and in parallel, how you can charge a battery. The next one is RC circuits, resistor and capacitors in series. And then the next one is electric hazards and safety. And then finally, 26.7 tells you how to take a ammeter, which is a device we can use that's really, really stripped down. It's essentially a piece of iron or some kind of ferromagnetic material, or at least diamagnetic material, in which you wrap some wire around, and then you set it on a spring-loaded system so that that little iron rod with the wires around it will tilt towards one side when current's going one direction and tilt towards the other way when current's going the other direction, all because it has some magnets in there. As you know, if you actually take and run current around a iron rod like that, it does make a magnet. And if it goes one way, it makes the end a north end of a battery of a magnet. If it goes the other way, it makes the south end of a magnet. Therefore, all you have to do is put the north end at one side of the scale and the south end of a magnet at the other end of the scale, and automatically it will go one way when the currents say uh, positive polarized, but when the current's going the opposite direction, the needle will flip the other way. Those are some of the devices, for instance, we used in mapping the electric fields in our labs, and they're very simple. They only go up to like 50 microamps or something like that, but all you have to have is a bank of resistors, and you can convert that to an ammeter or to a voltmeter. And actually, I called it an ammeter earlier. I meant a galvanometer. I don't know why I said the word. Oh, I see, because the word literally is ammeter was right in front of my face. But that galvanometer, that's just like I said, a magnet with a wire wrapped around it, set on a spring with a scale that's been calibrated. You can just add resistors to it and make it a voltmeter for any size voltage you want. You can make it an ammeter for any size current you want. So we may or may not cover that. I love that section and I want to cover it, but sometimes we have to skip it for time constraints. So, the first equation your book brings out is the terminal voltage equation. So, what we have to do when we're picturing modern batteries is we picture this picture I have right here. You can see I sort of drawn a double A or triple A battery with the circuit diagrams inside of it to show what it is. What we have here is a battery that has a certain voltage that I wrote as that fancy script E or script epsilon. That is the symbol we generally use for electromotive force. And that was, in some sense, what we initially called voltage before we had a true a good understanding exactly of what all electricity and magnetism was about. We just called it an electromotive force. And it's a bit of a misnomer, obviously, because it says force right in the name, and it's not a force. It's actually measured in volts, which is joules per coulomb. So that's what that E is. And the way we model batteries is we assume that they have not only a perfect battery inside, like you see here with an EMF E, but it includes an internal resistance, which we call lowercase r, so that when you actually draw current from it, the voltage will actually drop from E to E minus IR, where I is the current going through the internal resistance R. So we're just going to jump on this by solving this problem. It says a 60 ohm resistor is connected to the terminals of a 1.72 AA battery whose internal resistance is 0.35 ohms. A, what is the current in the circuit? B, what is the terminal voltage of the battery? C, how much power is dissipated by each resistor? So that's what we're going to do in this particular example is we're going to solve that information, solve for those quantities. So our solution, again, includes our relevant equations, which is VAB is equal to E minus I times R, where E is the electromotive force and R is the internal resistance. We are also making use of the fact that R in series, well, actually, I should say it like this. I'll say R equivalent sub S, meaning the equivalent resistance in series is just R1 plus R2 plus dot dot dot. And we're going to make use of that as well. We're also going to make use of Ohm's law, which says V is equal to I times R. And we're going to make use of the fact that the resistance R of the circuit is 60.0 ohms, and the internal resistance, lowercase r, of the battery is 0.35 ohms. And finally, the EMF of the battery is 1.72 volts. So we'll start off with part A. Part A, we want to know what is the current. I'm going to draw the circuit really quickly just to give you an idea of what I'm talking about here. So what we have is a ideal battery that has no internal resistance that provides an EMF given by 1.72 volts, but it is in series with a itty bitty resistance 0.35 ohms, and then the wire goes up, runs into our load, which is that resistor there, and that one has a resistance of 60.0 ohms. So that's our real circuit. What we know is the total voltage, 1.72 volts using V equals IR, is equal to I, the current going through the circuit, which I will say is right there, times the total resistance. Now the total resistance, since the lowercase r, the 0.35 ohms, is in series with the 60 ohms, we're going to say the total current is 60.35 ohms, and technically the 60 was only specified to one decimal place, but the 0.35 ohms was covered to 100 to two decimal places. So technically that 5 is not really a sig fig, but I'm going to keep it either way. And right now I can say the current in the circuit is equal to 1.72 divided by 60.35 ohms, and that gives me 0.02850 amps. So I did my typical thing of using at least two extra sig figs. In this case, it's the two zeros. We did have three sig figs divided by three sig figs, so this is the correct number of sig figs, and that's the current through the circuit. Does that make sense to everyone? Next, for part B, we want to know the terminal voltage, and we know that the terminal voltage, V terminal, which I wrote up there VAB, but either one's acceptable. V terminal is E minus I times R, so that's going to be 1.72 volts minus 0.02850 amps times 0.35 ohms, like that. You can see the IR is just another implementation of Ohm's law. So we finally get that V terminal. And remember, this is the terminal voltage when it's actually under load. So you do expect it to be a little bit below 1.72, of course. This is going to be 1.72 minus parenthesis 0.02850 times 0.35. That's going to give me 1.72 volts minus, now in this case, 0.02850 0.500 times 0.35. That gave me 0.009975. Uh, so I would call this 0.009975. Technically, we only had two sig figs there, so I would have to round it there. And you can see, in order for it to have any effect, I have to assume that the 9 that's the leftmost is going to be rounded up to 1 in the second decimal place. So ultimately, we get that the terminal voltage is just 1.71 volts. That makes sense? Feel free to ask me any questions as we go along if you have any. Now, the last part is we want to calculate the power dissipated by each resistor. I will tell you in general, it's always the best practice when especially when you're working on, say, test questions. It's best to use, if you can get away with it, use only the values that were given to you in the problem. So, in fact, if you solved part A or part B of the problem and you were able to determine a current or voltage or something like that, it would be better to find a way to use the information they gave you as opposed to using those calculated values. So we'll try to do the same. I'll remind you, even though I didn't put it up there in the solution section, that the power is equal to I times V, but that would require us to use I, which we calculated. We could also use power is equal to I squared R, but that would require us to know the actual current. Again, we calculated that, so that's not as helpful. But we also have V squared over R, where V is the actual voltage drop across the particular resistor R. And if we use that, then we're only using uh, well, in that case, we're actually using V squared for the whole battery. So that wouldn't be ideal either. So I guess I'm pretty much going to have to go ahead and make use of either the current that we calculated or the voltage that we calculated using the current that we calculated. So obviously, it'd be better to use a single calculated quantity as opposed to one that was doubly dependent on a calculated quantity. So, for instance, if I used I times R for the 60 ohm resistor, I'm using I, which I calculated, and then I'm using I times R, which I also calculated, so that wouldn't be as good. So I think I'm going to go ahead and stick with P equals I squared R. So P for the internal resistance is equal to I squared times lowercase r. That is 0.02850 amps squared times 0.35 ohms. So 0.002, or excuse me, 0.010, sorry about that. 0.028500 times 0.35. Ooh, excuse me. I got square at first. That would have been bad. So squaring that and then times 0.35 is only going to give me two sig figs, but it gives me 0.00028 and then I want two extra sig figs, so I'm going to call this a 3 here. And that's two extra digits that aren't significant, and that is in watts. And that is the power dissipated by the internal resistance. So you can say that's 2.84 or 0.284 milliwatts if you wanted. That would be fine. Now I'm going to do the same thing. This time I'm going to do it for the other resistor. So P of big R is I squared times big R. So this is 0.028500 amps squared times 60.0 ohms. 0.02850 squared times 60 gives me 0.04875. There's my extra sig figs there. And this is watts, and that's the resistance, or excuse me, that's the power dissipated by the resistance big R. So just to talk about exactly what that power is, because I'm not sure I've made a good conceptual case for what it is, but here's one way you could imagine it. And I don't recommend you doing this for hopefully obvious reasons that you'll see in a second. But if you were, for instance, to take a calorimeter and fill it up with a certain quantity of water and put a thermometer in it, wait for it to reach equilibrium, and let's say it's like 20 degrees Celsius once it reaches equilibrium. Now, if you somehow were to take this resistor, the 60.0 ohm resistor, if you were to submerge that in the water, and there's the reason why you might not want to do this at home, okay, while it's connected to the battery and all that good stuff, what you would find is that that amount of heat, which is 48 milliwatts, would be capable of increasing the temperature of the water exactly consistent with calorimetry methods that we learned in chapters 18 or 17 and 18. Okay. So it literally is a heat that's put out by the resistor. So if you put it in something like water, that heat could be used to warm up the water. And in fact, it's a certain amount of heat every second. That's why it's measured in watts. Hopefully that makes sense. Feel free to ask me any questions. Are we good to go on that one?
Good to go.
Okay. All right. So the next part, I actually left the space in case I couldn't fit that one, which I really should have done for the first one. So I left this space above this to do in case I ran out of room there. But that obviously is not an issue. So now I'm going to take and move this up. So up here. So this is example 3, and what it lacks is the drawing. So that's the only part. It says, which configuration of car headlights yield the most light? Assume they are identical. So I'm going to draw a configuration of headlights that you can analyze and think about yourself, and then I'm going to analyze it so you'll understand. First off, I have P is equal to IV is equal to I squared R is equal to V squared over R. We know V is equal to IR, which is how I got those different versions of P. But that's pretty much it. What I'm also going to do is I'm going to assume the amount of light produced by a light bulb is proportional to the power of the bulb. Now, that might sound like duh, but what I want you to understand is, for instance, when we talk about a 100-watt incandescent light bulb, I've seen suggestions that it might be a couple percent of the actual 100 watts of an incandescent light goes to actually light energy. All the rest of it is parts of energy and parts of the electromagnetic spectrum that's not within the visible spectrum. So it's completely wasted, more or less. But whatever that percentage is should be about the same for all identical light bulbs. So if it is only 5%, then doubling the power still doubles the power for the 5% part. So that's what I'm saying here. Now I'm going to go ahead and draw the figures that I'm talking about. What you can imagine is a 12-volt battery. This is supposed to be like a car battery. Okay. And one option is you put your light bulb there, and then you put your other headlight bulb there. And the other, well, by the way, we'll say this is V. 0 is the voltage of that battery, which actually equals 12.0 volts for a car, but I'm just going to treat it as a symbol V0. I'm going to say that P0 is the power of one light bulb, and I'll say P0 0 is also the power of the other light bulb. And now I'm going to do the same thing for a different configuration. That different configuration is again V0 equals 12.0 volts. And now this time I'm going to run along in series for the light bulbs. So this is also P0 and this is also P0. And that's what we're going to try to figure out. I'm going to call this little current right here I1. I'm going to call this little current right here I2. And I'm going to call this current right here just plain I0. Okay. So now my goal is, because I said we're going to assume that the power put out by a light bulb is directly proportional to the amount of light. Again, it's not necessarily going to be 100%, but whatever it will be consistent. So if, for instance, one light bulb is putting out at 5% and the other light bulb is putting out at 10%, then that's consistent with the power being twice as big in the 10 watt situation as compared to the 5 watt or the 5% situation. Okay, so hopefully that makes some sense. So first off, we'll try parallel. So what we have here is a total resistance given by 1 over R equivalent. Well, actually, I can't even do that yet because I can't figure out what the resistances of the light bulbs are. But what I can do is, okay, I can say P0 is obviously equal to, actually, I should probably say there's 0, and I'll call these P0s in the series. I'm going to call them something different than P0 because there's a chance, obviously, that they're going to be a different output in the different configurations. So I'll call this one PS. Whoa, Dilly. I'll call it PS and that one PS as well. By symmetry, they have to be identical to each other in the single circuit. But if you compare one light bulb in the circuit on the right to the light bulb to either light bulb on the circuit on the left, they will not necessarily have the same power. That's the whole point of the question, is figure out which one does the more power. So what we're going to do is we're going to say P0 is obviously equal to I squared times R, and we'll call R0 the resistance of the light bulbs. We're going to pretend like they're all the same. So I'm going to say R0 is the same for that bulb and that bulb. And what that means is, and actually, by the way, I think y'all know enough that I1 and I2, do y'all agree that these would be the same currents?
Yeah.
Yeah, just from symmetry, uh, we're saying the two light bulbs are identical, so their resistances should be identical. Therefore, we've got two identical resistors in parallel, and we know that their voltages are automatically equal. Their resistances are now equal, and since the resistances and the voltage are equal, the current through them must be equal. So in this case, I'm going to say P 0 for the parallel is I squared R0, and that's the power put out by a single resistor, or by a single light bulb. But we have to figure out what I1 is. So what we can do is we can realize that 1 over R equivalent is 1 over R0 plus 1 over R0, uh, which means that well, I'll go ahead and show you the extra step, which equals 2 over R0. Therefore, R equivalent is R0 over 2. So by putting them in parallel, we've actually found the net resistance to be a little bit smaller for the circuit. So now we can figure out that I will call this one I total. So I'm going to put another current right here. I'm going to call this I total. I can say that I total times R 0 over 2 is equal to V0. That allows me to figure out what I total is in terms of things we know. So I'm going to say I total is equal to 2V0 over R0. Now, what we know is that I total is equal to I1 plus I1, which obviously equals 2I1. Therefore, I1 is equal to I total over 2. Okay. So I've now figured out what I total is, and now I can put in exactly what I1 is. So I can say P0 is equal to the current going through the light bulb in the parallel system squared times the resistance of the light bulb. And the I1 we just learned was in fact half of I total. So I'm going to say I total over 2 squared times R0. But we also figured out that I total is 2V0 over R0. So now I'm going to put 2V0 over 2R0. The 2 was already down there. That's going to be squared, and then that times R0. So what I see now is ultimately I get V0 squared over R0 is the power for one light bulb in the parallel case. So two lights imply P total parallel is equal to 2V0 squared over R0. So that is one result, and that's the result for the parallel part. Now let's try the series. So what I just calculated, by the way, is the an estimate of exactly how much power is being dissipated, and therefore you have some fixed percentage you'd multiply by that value to determine how much light it is. That same fixed percentage will be applied to every one of them as well. But the main thing is the one that has the larger P is also going to have the larger light put output because it's multiplied by the same percentage. So now with the series one, what we know is that R equivalent in series is equal to R1 plus R2 plus dot dot dot. So R equivalent series is just going to be 2R0. So the net resistance for the circuit is just 2R0. And using Ohm's law, we can say V0 is equal to I0. Notice I'm using I0 because the diagram on the right says that's the total current. I0 times the resistance, which would be 2R0. That tells us that I0 is actually equal to V0 over 2R0. Now, the resistance again, or excuse me, the power again for a single light bulb, PS, is going to be, uh, we can either figure it out in terms of I squared, which in this case would be I0 squared times R0. So now that I know R0 or I know I0, I can plug that in. That's going to be V0 over 2R0. All that's going to be squared and then times R0. So now I get V0 squared over. Now the 2 in the bottom actually becomes a 4, and the R0 becomes R0 squared, and it's times the R0. So in this case, I get 1/4 V0 squared over R0 is the power for a single bulb. So now I can say P total in series is equal to 1/4 V0 squared over R0 plus 1/4 V0 squared over R0, which equals 1/2 V0 squared over R0. So we can see that in this case, the two light bulbs being in parallel is a better choice. It puts out more light. In fact, it puts out a factor of 4 times more light. So uh, the parallel bulbs or headlights produce 4 times, oops, as much light as the series. Can anybody think of another advantage of parallel over series? Remember Christmas tree
So if
lights.
yeah, if one of them goes out, the whole circuit doesn't go out.
Exactly. So yeah, when you have them in parallel, one light bulb goes out. That's okay. Not only that, it actually sort of will make that one light bulb a little brighter, which is going to make that light bulb burn out a little quicker. But still, at least it's brighter and trying to do something to bring it back to normalcy. So it's somewhere between a single headlight running by itself and both headlights running. So, any questions on that one? That is not a trivial way of solving it. It's the way my brain works. It's the way my brain thinks, and I like it. And it gives very definitive answers. Like I know not only that it's 4 times as much, but I know that it's exactly 4 times as much. Not 3.99, not 4.01. It's 4.000 to an infinite number of decimal places. But the other way of thinking about it for you guys is conceptually you know that when you put the two resistors in series, or excuse me, in parallel, then the net resistance of two of them is actually smaller than the resistance of either of them. Since that's the case, you've got a lot more current to work with because the voltage is dictates with the resistance dictates what the current will be. So now that we've cut the current down or the resistance down by more than a factor of two, that means the current is going to go up by more than a factor of two. So that's a reason for the power to be a little bit more intense with the parallel lights alone. Another one is that they both get the full 12 volts. So if you think of power as I times V, the parallel one has I larger, and the parallel one also has V larger. So you do expect P equals IV to be bigger for the two parallel light bulbs. Whereas if you think about the two in series, each of them only get a half of V0 for the voltage. But in addition to that, the current's going to be smaller because the current is based on the voltage, which is 12, and the total resistance, which now is going to be like 4 times as much as the resistance that the two had in parallel. So that's going to bring the current down too. So both the current went down and the voltage went down. In fact, the voltage across the individual light bulbs would just be 6 volts and the current, of course, will be smaller too. So that's conceptually a couple of reasons why the parallel is better. Hopefully, some part of that explanation makes more sense to you. Hopefully, anybody have any questions? All right. We're going to go to another example now, and what I'm going to do is find the equivalent resistance as well as the current drawn through each item. So I'm going to draw a figure for starters. I'm going to write that this is a battery, and this battery has a voltage of 12.0 volts. I'm going to imagine that it's going to run around. Oops. Oops, I did not mean to do that. I guess I can't turn that around now. So I'm going to imagine that it comes around, runs into a resistor, and then after that resistor, that wire breaks apart and runs into a bank of parallel resistors like this. And then the whole wire comes back to the battery as such. I'm going to say that this one is 100 ohms, and I'm assuming all of these are 3 sig figs. This one's going to be 200 ohms, and this one's going to be 300 ohms. What I want to know is, God darn it, what I want to know is V1 is question mark. That means the voltage across the 100 ohm resistor. V2, the voltage across the 200 ohm resistor. V3, the voltage across the 300 ohm resistor. I also want to know I1. I also want to know I2. And I want to know I3. And I want to know R equivalent for the whole circuit. Okay, so that's the results I wish for. And this would technically be what, example 4? So first off, when you're doing these, it's just like when we did them with capacitors. You find any two resistors, or in the case of capacitors, it was capacitors, but you find any two resistors that fit the definition of series or parallel. If you happen to find more than two that all meet the criteria of being in series or of being in parallel, then you grab as many of them that all meet that definition at one time, and then you go on to another set and then go on to another set. Right now, it looks like only the 2 and 3, the 200 and the 300 ohm resistor, meet the criteria for a parallel set of resistors. So I'm going to do that. I'm going to say solution. And here I'm going to make use of V is equal to IR. I'm also going to make use of 1 over R equivalent parallel is equal to 1 over R1 plus 1 over R2 plus dot dot dot. And I'm going to make use of the fact that R equivalent in series is R1 plus R2 plus dot dot dot. And we'll go from there. So now 1 over R23, meaning the equivalent resistance that would replace resistor 2 and resistor 3, which means the 200 and the 300 ohm resistor, is equal to, this program is really making me mad, is equal to 1 over 200 plus 1 over 300. Now, we know that's not necessarily the nicest bunch of fractions to deal with, but we also know that 200 does not go into 300. But if we tried 200, or excuse me, 300 times 2, that would make 600, and 200 does go into that. So I'm going to multiply the 300 by 2 over 2, and I'm going to multiply the 200, 1 over 200 by 3 over 3. So this is going to be 3 over 3 times 1 over 200 plus 2 over 2 times 1 over 300. That's going to give me 3 plus 2 over 600, which equals 5 over 600. Therefore, R23 is equal to 600 divided by 5. And of course, 100 divided by 5 is 20. So 6 times 20 would be 120. So the equivalent resistance is 120 ohms. So that means now our circuit looks like this. And that one's pretty straightforward. We can see both of those resistors are in series. So now I can say, in this case, I'm just going to call it R equivalent because this is the final resistance that we're replacing all of them with. So R equivalent is equal to 100 plus 120, which equals 220 ohms. And now all of a sudden we have the answer to one part of the question. The answer is 220 ohms. Now, that's nice because it turns out that if you just sort of looked at the circuit and said, as far as the battery knows, it just sends out a certain amount of current, and that current would be what we call I total. So I'm going to call this IT for I total. Now, the equivalent to that is that basically we have a 12 volt battery in series with a 220 ohm resistor. So that still, of course, has the same current I total. If it didn't, then we didn't find the equivalent resistance. If it behaved differently with this 120 or with this 220 up there, then clearly that's not equivalent resistance because the definition of equivalent resistance is one that makes the battery do exactly the same thing. So with this, we can just use Ohm's law, and we're going to say 12.0 volts is equal to I total times 220 ohms. That gives us I total, which we weren't asked for, by the way, but I'll box it off anyways because it's something worthwhile having. So I'll take 12.0 and I'm going to divide it by 220, and that gives me 0.054 545. Okay, that's an additional two figures beyond the sig figs, and that's in amps. So again, I'm going to box that off, even though we didn't ask for that particular answer. But what we know is that the I total is actually got to be I1. Does everybody understand that? I total is the current going through the 100 ohm resistor.
Yep.
Good deal. Conservation of charge says I total is equal to I1. So I1 is equal to 0.05445 amps. Now we're almost done here. What we see now is this I1 slash I total is going in and it's breaking apart like that. So part of it goes up to the 200, part of it goes to the 300. In fact, you've probably learned by now that the smaller part of the resistance will go to the 300 ohms, and the larger, or excuse me, the smaller part of the current will go to the 300 ohms, and the bigger part of the current will go to the 200 ohms. But the main thing is we know that I should write this in purple. The main thing is we know that I total I1 or I total is equal to I2 plus I3. Again, I2 being the current that goes through the 200 ohm resistor, and I3 being the current that goes through the 300 ohm resistor. So I'm going to use this as equation 1, but I also know that since the 200 ohm and the 300 ohm are in parallel, then they have the same voltage. So that means V2 is equal to V3, and V2 equals V3 gives us that I1 R1 is equal to, or excuse me, I2 R2. Let me just erase that. I2 R2 is equal to I3 R3. Therefore, we can say that I3 is equal to R3 over R2. Oops, backwards. Therefore, we can say that I3 is equal to R2 over R3 times I2. And of course, that's 200 over 300 I2, which is 2/3 I2. Now, I can call this equation 2, and I'm going to plug 2 into 1, and that's going to give me I1, which we already knew was 0.054545 amps, is equal to 2/3 I2 plus I2. Now, 2/3 plus 3/3 is 5/3. So we'll say equals 5/3 I2. And now we can see that I2 is 3/5 of that current. So I'm going to say times 3 and divided by 5. That gives me I2 is 0.03272, and that's my extra sig figs or my extra non-sig figs. That's the current I2. And then I3, of course, is just going to be from the same equation. I3 is equal to 2/3 I2. So if I multiply this times 2 and then divide it by 3, I get 0.021818 amps. And that is I3. And of course, V1 is equal to I1 times R1, V2 is equal to I2 times R2, and V3 is equal to, ooh, that's supposed to be a 3, I3 times R3. So time's up. I just wanted to show you what you had to do for that last part. So I just wrote it there. It should be fairly trivial, but when you do it, you want to make sure that it's consistent with the other considerations, like if you go in a closed loop, basically the sum of the voltages up and down should add up to give you zero. So, anyways, that's enough for this. You guys are welcome to leave. I'll wait for the last person to go in case anybody has any questions, and I'll probably finish out this problem after you leave just to have it on the recording.
Sounds good, Professor. No questions here. I'm running to a makeup lab, so I'm gonna
That's cool.
get in.
Thanks, Matt. Have a good one, bud.
Yeah, yeah, yeah.
Ah, see you back there. What you barking at, buddy? All right, just finishing this up. V1 is equal to I1 times R1. R1 is 100 ohms, so it's just multiplying by 100. I try to keep my numbers in pods of 3. So this 4, 5, 4 should be a pod of 3, and then a space 5, like that. Those two are not sig figs, and that's equal to V1. So I'll box that off. And then V2 is similarly calculated. And this one's going to be 0.032727 amps times 200 ohms. 0.032727 times 200. That one gives me 6.5454. Oops. Volts. So V2 is equal to 6.5454 volts. That's V2. And then V3 is equal to 0.021818 amps times 300 ohms. And this value gives you 0.021818 times 300. That gives me the exact same current, which we expected anyways, 6.5454 volt, excuse me, voltage. We expected the same voltage anyways because it was in parallel. And this is equal to V3, so we've got all that figured out. And this all seems consistent, and we're done with this example. Again, thanks for coming, everybody. Hope you enjoyed it. Hope it helped. And we will press on. I will be posting more videos over the weekend to try to get us ahead a little bit. So please subscribe to my channel at least for the last couple of weeks of class so you can see when I post something, and then you can watch it because we're going to have to speed up a little bit to get at least through chapter 30. Thanks for your time. Bye bye.